I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for the students. Just pray that you just guide our work today, Lord. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Okay, so today I want to talk to you about residues and how to use residues to calculate some integrals, hopefully. So let's get to it. The central tool that is behind the scenes here is Cauchy's residue theorem. Cauchy's residue theorem states the following. Basically, if you've got some closed contour, right? And so this whole thing is D, right? And inside D, you've got some, maybe, say, Z1, Z2, Z3, maybe you got K of these singularities, ZK. So let's suppose that F is holomorphic on D, and the boundary of D, and D I'm thinking of D as a domain. So in when I say it's holomorphic on the boundary, I mean that it goes a little, it's holomorphic a little bit beyond the edge, all right? Except at the isolated singularities Z1, Z2, Zk, then, well, let me put the then up here. You have the integral of f of z dz over the boundary of D is equal to what? It's equal to 2 pi I times the sum of the residues. So to calculate the integral of a function around some curve, all I have to do is figure out, are there singularities inside the curve? If there are singularities inside the curve, I calculate the residue of each one of those and take that sum of the residues. That gives me the integral. In particular, a case that's been with us for a while is the case that the function is just plain old holomorphic on all of D, in which case there are no singularities, and we get back to Cauchy's theorem, that the integral is 0, right? But when there's a singularity, we get non-trivial contributions from the singularity, as we've discovered in the last few classes. Now, so it's of crucial importance that we learn how to calculate these residues as efficiently as possible, and there are 4 rules to do that. So rule number 1 states the following: if f of z has simple pole at z equals to z naught, then the residue of f of z at z naught is simply equal to the limit as z goes to z naught of z minus z naught times f of z. Rule number 2, if f of z has double pole at z naught, then you can calculate the residue of f of z at z naught by taking the limit as z goes to z naught of the derivative. d dz of z minus z naught quantity squared times f of z. Rule number 3. Rule number 3 states that if f and g are both holomorphic at z naught, and if g has simple 0 at z equals to z naught, then the residue of the quotient at z naught is just equal to f of z naught divided by g prime of z naught. And finally, rule number 4. Rule number 4 states that if g has a simple pole at z naught, kind of a special case of rule number 3 in some, really, simple pole at z naught, then the residue of the reciprocal of g, 1 over g of z, at z naught is just equal to 1 over g prime of z naught. Really, that's just a rule number 3 with f set equal to 1, right? These are the rules.
Is that simple 0?
Simple 0, sorry. Right? Otherwise it wouldn't make sense. Now the proof of every one of these is just based off basically the sort of generalized factor theorem we had for polynomials, for power series, and those basic structure theorems we had about poles of order n and such. Proof in the notes. They're not especially exciting. I think you can prove every one of these if I asked you. So let me show you some examples. And so part of the point of these examples is just to showcase the simplicity of these rules. We have done this first example with partial fractions before, and it was not as simple as what I'm about to show you. What I'm about to show you is just maddeningly simple. The calculation of the residue here, I can't emphasize enough how easy this is. So suppose you have g of z is equal to z squared plus 1, right? Notice that g of I is equal to 0, but g prime of I is equal to what? See here, so yeah, 2i, right? Which is not equal to 0. So therefore, z naught equals to I is a simple 0. And so the residue of 1 over z squared plus 1 at I is simply 1 over 2i. Before I broke it up into a sum of two rational functions and so forth. It was more involved. Let's see here, another few examples. If we look at the residue of the cosine of z divided by z minus 3 times e to the z, at 3, what do we get? Golly. So here, identify the denominator as g of z, right? If you plug in what? If you plug in 3, you get 0, right? But if you calculate g prime of 3 for the denominator function there, you do not get 0, you get non-zero. So in fact, that has a simple 0. The denominator has a simple 0 at z equals to 3. And clearly the denominator and the numerator function are holomorphic at 3. So we can use rule number 3. Rule number 3 says, hey, you just plug in 3 into the numerator, and you divide by the derivative evaluated at 3. What's the derivative of, so g of z is what? G of z was z minus 3 times e to the z. What's the derivative of that? G prime of z is e to the z plus z minus 3 times e to the z, right? So if you plug in 3 into this, that term vanishes and you just get e to the 3. There you go. So I'm working backwards, right? This is an example of rule 4. This is an example of rule 3. Let's look at an example of rule 2. Suppose we wanted to calculate the residue of, I don't know, sine of z divided by, I don't know, z cubed minus 6z squared plus 9z at minus 3. Oh, yeah, this is not a, sorry, as I'm currently, I mean, I find myself, guys, most often using rules 3 and 4. So this isn't really a good example yet for rule number 2. To make this a good example for rule number 2, I should do something like put a, you know, I don't know, say 7. Sure. Even so, I don't. Let me make it more blatant. More blatant. Suppose you have something like e to the z divided by z plus 3 quantity squared times the cosine of z. It's easy to see that this has a pole of order 2 at minus 3 because if you look at f of z equal to 1 over z plus 3 quantity squared times e to the z over cosine z, what do you have? You have, this is, you know, n equals to 2, and this is holomorphic at z equals to minus 3, right? So by our structure theorems we talked about in previous classes, that is clearly something with a pole of order 2 at minus 3. So I can apply rule numero 2, and this is going to be the limit as z goes to minus 3 of the, what? Derivative with respect to z of what? We multiply this by z plus 3 squared. What does that do? Yeah, I mean, exactly. So you're just left with this lovely, here's the leftover piece. I mean, these rules are really not mutually exclusive, right? Like I told you guys, my personal preference is almost always to use rule 3 or 4 for specific problems because there's no limit in the formula. And I mean, the limiting process here is kind of stupid as well. Let's see here. What happens? You get limit as z goes to minus 3. We got e to the z cosine z minus, well, plus e to the z sine z divided by cosine squared z by quotient rule, right? So apparently the residue here is e to the minus 3 times the cosine of minus 3 plus the sine of minus 3, all divided by cosine squared of minus 3. There you go. So there's an example of rule 2. I will give you an example of rule number 1, and then we'll move on to integration, all right? So here's rule number 2 exposed. Rule number 1. Here's a kind of typical example, something like this. Suppose you wanted to calculate the residue of cosine of z over z minus 2. So you go, aha, this has a simple pole at 2. That's clear because it's an analytic function at 2, which is cosine. Right? Cosine's entire, it's analytic everywhere, so it's certainly analytic at 2. And you're dividing by z minus 2. So that is exactly the form of something with a pole of order 1. It's a simple pole. And so I use rule number 1, and I take the limit as z goes to 2 of z minus 2. And you see what happens. I mean, see the whole point here is that these guys cancel, right? Cosine of 2. What's that? Which one?
The one you just did.
I said it was going to be difficult.
Oh, am I just wondering? Okay, never mind, I won't speak.
I might have said
I
that.
thought you said it was going to be a difficult example.
I might have said that, but I may have said that, but if I did, I think the difficulty was with my saying. Let's see here. All right, so there you go. That's how to calculate residues. Now, of course, you can fall back on the more general series calculations, that we did, and you should read the notes and learn how to derive these, but they're really quite straightforward. It's nothing more than manipulation of the Laurent series to clear out, z minus z naught to the nth power or whatever you need. It's just what do you need to select the minus 1 coefficient of the Laurent series. That's what these rules are based on. Excuse me.
Are there more generalized ones for nth order poles, like using derivatives?
We don't care. So, but yes, of course, you can select other components by different kinds of rules. Who's taking differential equations? So you guys, you did the Frobenius method yet? When you get to the Frobenius method, which is, we look at this something called a regular singular point. In that, you define these p and q functions. Like there's something very similar to this in that. There's something kind of like this, I think, to define the p. And there's something, not this, but something similar to that, but it's you multiply by x minus x naught squared and take the limit as x goes to x naught. That actually is, there's something about a pole of order 2 in the study of the Frobenius problem in differential equations. So there are examples in math where we do something other than just look at the minus 1 term in a meaningful way into an application. But for us, since everything is really going to be centered around this Cauchy integral, the Cauchy residue theorem, the residue is where it's at for us.
Well, right, but I'm saying like if the function has a triple pole, a quadruple pole,
Oh.
is there like a more generalized method to calculate the residue?
Yeah. There's a generalization of that to higher poles. Yeah. Indeed, there is. That sounds like a really interesting test question. I like that.
Or using it.
I like that. Section 7.2. What is the generalization of rule, what is it? Generalize rule 2 to poles of order n. Yeah, I like it. Section 7.2, integrals featuring rational functions. So, excuse me. Come on. That's not what I want. Oh, this is what I want. Oh, I was thinking something else. I was thinking something else. Oh, these are easy. Section 7.3 is where the fun is at. Fine, we'll do section 7.2. All right, integrals involving rational functions. So, problem. Suppose you wanted to figure out what's the integral, say from minus infinity to infinity of dx over x squared plus 1. Now, you can do that, right? Because that happens to have an antiderivative of inverse tangent, right? But I want to show you a different way, a really different way. And this different way I'm showing you will allow you to integrate things that you might not have even thought about trying to integrate. So here's the approach we're going to take. We're going to say, hey, this is really the integral along the line segment minus r to r, right, of dz over z squared plus 1, right, where you're taking the limit as r goes to infinity. And if you have a little imagination, you can look at this half circle, like so, of radius r, right? So this bottom piece, right, is the minus r to r, which I will shortly illustrate in red. That's just a line segment on the real axis, right? That's this piece. All right? And then, if we're going to be counterclockwise oriented, that's an important thing, by the way. These are counterclockwise oriented, right? The outer boundary. So counterclockwise means I got to go this way, right? You can see that there's also a circle, a half circle, if you will, of radius r. I'm just going to call it c sub r for the sake of this example. All right, so if I look at this as being my domain, if you want to, I could put a little sub r dependence on it, because here's the domain for radius r. Then we could say, okay, well, the integral over the boundary of the domain of radius r of, dz over z squared plus 1 is equal to what? It's equal to the integral from over the line segment, right? Plus the integral over the half circle, right? You guys with me? But what else is it equal to? If we make a little assumption, let's assume that r is greater than, I'll be greedy, greater than 2. I'm interested in the limit as r goes to infinity, so surely there's no harm in saying that r has to be bigger than 2. Why would I do that? How can you calculate this integral directly without so much as an integration? Residue, yes. Oh, look over here. That function has a simple 0 at I. And where else does it have this function has singular where? Plus or minus I, right? So I, let's say, is here. I is here. And then minus I is out here, right? Minus I doesn't count. It's outside. Doesn't contribute to the integral. Only I contributes to the integral.
You should make the radius 7.
I am the only one that matters. Let's see here. What's that? Make the radius 7? No.
See, for some reason,
I will not. I will not. I will not succumb to the corrupting influence of Joe in this class. All right. So this is 2 pi I times the residue of 1 over z squared plus 1 at I. But hey, as we were just mentioning over here by rule number 4, this is equal to 2 pi I over 2I. In other words, this is just pi. So I know the sum of this integral plus that integral is pi for any r greater than 4. You guys with me? So now, next step in the game here, but 1 over z squared plus 1 is what? Less than or equal to 1 over r squared minus 1 for z modulus of z equals to r, right? We have this because r is greater than 4. I mean, I could have made do with 1, right? So that's bound. That's our m. Therefore, by ML theorem, what do we have? The modulus of the integral over CR dz over z squared plus 1 is less than or equal to, apparently, what's the length of the CR curve? What is the length of a half circle of radius r?
Pi r.
Okay, yes. Sorry, I'll try to be less condescending in my questioning in the So we have that pi r over r squared minus 1 is a bound on that integral. What happens as r goes to infinity? This goes to 0 as r goes to infinity, right? Excuse me. But we can apply Cauchy's residue theorem on each half disk as the half disk grows to infinity, right? So, what's the answer? Putting together what I wrote in blue over here with our thoughts, we have now that the integral, the integral from minus infinity to infinity of dx over x squared plus 1 is equal to pi. And we calculated that without doing a single stupid integral. Right? That's weird, isn't it? I think that's bizarre. Of course, the standard solution isn't that hard either, is it? It's inverse tangent of x. As you go to plus infinity, you get pi over 2. Then you subtract the minus pi over 2 at minus infinity, so you get pi. I mean, it's not. This is an easy Calc 2 problem also, but I think it's nice to see how it works out in residue theory, yeah? Excuse me. All right, so if you look at this, right? Whoa, did I put my paper somewhere? I do. So there's nothing especially special about this example in the sense that this is example 7.22 in my notes. But you can easily, generalize this example. For example, example 3, 7.23 in my notes, I do essentially the same thing for, what's the difference? I put a 4 here. What does that do? Where is z to the 4th plus 1 equal to 0? Let's see here. So Minus 1 equals to what? Minus 1 is equal to e to the minus pi I over 2, right? So you divide that by 4, and you get e to the minus pi I over 8. That's one of them, right? And how do you get the rest of the fourth roots of minus 1? What's that? Oh, I think I did it wrong. What did I do wrong? I did something wrong here. Sorry, guys. Un momento. I don't know how I got this, but I don't know what I'm doing. What I did. The point is, this is e to the pi I over 4, I e to the I pi over 4, minus e to the I pi over 4, and then minus I e to the I pi over 4. Those are the fourth roots of minus 1. This is easily verified by just, if you take this and raise it to the fourth power, you get e to the pi I, which is minus 1. Now graphically, those are here, 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 and here on the unit circle, right? So only 2 of those figure in to our calculation this time, right? Now, inside the half circle residue, there's one here, right? And there's one here, roughly speaking, right? There's the e to the pi I over 4. And what's the other one that falls inside the residue? Supposing r is greater than some reasonable value. I think 1 will do it, actually. I think you rotate by 90 degrees, right? So it's the I e to the pi I over 4, right? Which again, geometrically, rotate by 90 degrees. There it is. Those are the 2 that fall inside the, so the critical issue when you're calculating one of these problems is to figure out which of the singularities of the function fall within the contour. Once you figure that out, then you use Cauchy's residue theorem, and hopefully you can show some interesting piece dies to 0. That's kind of a generic strategy. So essentially the same strategy is going to work for this problem as the one I showed you at the start, just I have to, make the appropriate adjustments. So this is 4, this is 4, this is 4, this is still 2 pi I, but now we have to add plus the residue 1 over z to the 4th plus 1, where? So e to the pi I over 4, and I e to the pi I over 4. All times 2 pi I. Don't forget your 2 pi I. Almost the same ML argument works, right? It's singular. It's singular at all these points up here I told you about, right? So somewhere you got to talk about singularities. Right? In fact, that's the first thing you should figure out, is where are the singularities for the function you're trying to integrate. So we do that first, figure out what I have to include in Cauchy's residue theorem. And then I decide, can I show that these things go to 0? Yes, I can, because, so there's the 4th, right? Now, what's the calculational, what do I need to do to actually figure out what the answer is? It's not pi anymore, right? Well, it might be, I don't know. I have to calculate these residues, right? So what are those? Z to the 4th plus 1 has simple zeros. It has 4 distinct simple zeros. So this is the easiest thing. We just, we use rule that I erased. What do? Just rule number Rule number 4, I think, is the tool to use here, which said what? The residue 1 over g of z at z naught was just what? It was 1 over g prime of z naught, right? Supposing z naught is a simple 0 of g. Okay, well, e to the pi over 4 is a simple 0 of that. So all I got to do is 1 over 4 z cubed, right? Evaluated at that, though. So it's 1 over 4. Well, I'll tell you what. I'll write one in between step. 1 over 4 z cubed evaluated at z equals to e to the pi I over 4 plus what? 1 over 4 z cubed evaluated at z is equal to I e to the pi I over 4 by rule 4. And so what does that give you? These details you can work out. Now we're back to like the first 2 weeks of the course, right? These kinds of details. They still matter. And it works out to pi over root 2. And so this is pi over the square root of 2. All right. There's a simple twist on this that you can do integrals of like cosine or sine over a quadratic. Maybe I'll talk about those some other day. The other idea I wanted to show you today was section 7.3, integrals involving trigonometric functions. Isn't it a relief? We don't have to calculate the whole Laurent series, right? We have these 4 rules. We just pick off the one coefficient we care about. You learn this technique, and you can do these kinds of problems, right? It's pretty straightforward, but to actually find all the singularities of, say, something that has like a sixth order polynomial in the denominator, it could be a pain, right? But the pain is a familiar one. It's that of factoring, right? So what I'm about to show you is really different. So I will give you the motivational calculations. All right, so here's the deal. If we're on the unit circle, parametrized by what? Z is equal to e to the I theta, right? So, okay, so on the one hand, that's cosine theta plus I sine theta, right? On the other hand, we also have that dz is I e to the I theta d theta, right? And of course, we also, let's see here, what can I say? Well, you know the modulus of z, I mean, you know z bar. Let's see here. See, how can you solve, I mean, I guess the question is, how can you solve for cosine theta and sine theta here? How about 1 over z, what's that equal to? E to the minus I theta, right? Which would be what? Cosine theta minus I sine theta? So if we wanted to solve for sine and cosine these relations, what would we get? What's z plus 1 over z? So focus on this, let's call this 2, let's call this 1. Focus on 1 and 2. How would you, if you add 1 and 2, what happens? Yeah, we just get 2 cosine theta, right? So therefore, cosine theta is 1/2 of z plus 1 over z, which of course is not terribly surprising because this is just e to the I theta plus e to the minus I theta. It's again, so I think once you see that, you're not surprised when I tell you that sine of theta is 1 over 2i z minus 1 over z, right? This is how z, cosine, and sine theta are related on the unit circle, for the parametrized unit circle. Okay. Fine. So then, let's try to do the following integral. There's a big difference between these examples and the ones I just did. The examples I did that involve integrals that go to infinity, improper integrals, right? So there's usually some piece you want to show vanishes by the ML theorem. Contrast here, these are just plain old definite integrals we can calculate using residue theory. Here it is. Integral from 0 to 2 pi d theta over 5 plus 4 sine theta equals what? So what you do is say, aha, I'm going to reinterpret this as a contour integral around the unit circle. Counterclockwise, okay? And I already have the roadmap over here for the substitution. What's d theta? So we got dz is equal to I e to the I theta d theta. Written in terms of z, that's I z d theta. So therefore d theta is dz over iz. dz over iz. There you go. One thing down. 5. What is 5 in terms of theta or z? I think it's still 5. Okay, so there we go. 4, that transforms easy enough. 4. And then sine theta is 1 over 2i z minus 1 over z. Now we own this integral now. We put it in it's in our house. We have the right to shoot it if we want to. Is that allowed? Is that allowed in Virginia? Can we shoot people in our house? No? What if they're bad people? Only tase them? Oh.
Shoot them with the dart.
My children have been shooting me. Someone should tell them the laws. Let's see here. Mostly with Nerf stuff, but still, you know. All right, so this is dz over 5iz plus 2. I'm canceling this to give me 2, and I'm multiplying through the I, so the I cancels 2. Z times z minus 1 over z. Not done yet. Let's finish cleaning that up. This is the integral over z equals to 1 of dz over 2z squared minus 2. Oh, these just cancel and give me the minus 2. I should probably write the plus 5iz minus 2. And now I can use Cauchy's residue theorem. All I got to do is figure out where are the zeros of this quadratic. Now, it's been a while since I've looked at this problem. I like to come fresh to class, you know. If I prepare ahead of time on these kinds of things, it always goes badly. So, I don't know if this is going to work or not. I'm right where you guys are. Can we do this? Is it possible? All things are possible. Okay, I'll take it. So plus 2i and plus I. Sharon is right. All things are possible. You just have to have some imagination. Let's see here. So plus iz plus 4iz plus 5iz, 2 to pi minus 2. Okay, good. So if you look at then the unit circle, whoop, this is 0, what, at z equals to minus I over 2, which is like here. And this is at z equals to minus 2i, right? Which is down here. We don't care about that. So all we got to do is calculate 2 pi I, the residue of 1 over 2z squared plus 5iz minus 2 at minus I over 2. But hey, this is a simple 0, so why don't we just differentiate it and make use of rule 4? That's 1 over 4z plus 5i evaluated at z equals to minus I over 2, which is 2 pi I times what? We got 7i? I think it's 7i. What'd I do? Oh man, how did I get a minus there? Oh, because it's minus I over 2, right? Duh. Duh. 5 minus 2 is what? 3, right? Okay, so there you go. 2 pi over 3.
Shame, it's good for 7.
Ah.
3, right? We could do it.
It's 7, but 7's equal to 3.
Right.
Okay, there you go. All right. What's that?
Were we able to do it?
We were able to do it. All things are possible. That's true. Now, think about this. If you wanted to be like a really weird Calc 2 instructor, right? You could black box this thing. You could just like teach it as an algorithm. You do this, you do that, you do this, and then the answer. Like this really could be. I would have to think about it for a while. Like, how would you rewrite this? Remove all of the complex analysis from it, right? And just make it into some stupid calculus 2 black box kind of thing. Like you could do it. I don't think it's a good idea, but you could possibly do it.
Be better than that weird, like, tan theta over 2 6.
How many lectures did I get through today, Lorenzo?
Approximately 1.
Dang it. I feel like I got through 3. Man, are you serious?
It's gonna be on your professors like Black Friday, and then you
No. We're over with that. It's done.
No, please don't tell me it's Monday. I don't think I can handle that.
It's actually Friday of next week.
There is no more Friday song. That is forbidden. That 15 minutes of fame is over. It's over.
At least she was thinking I did English.
You're going to regret saying that.
What's today?
It's approximately Friday the 13th.
Oh. Hey, I covered one of the topics that's on the 13th. I am now on track. I only have to cover branch points and fractional residues today in the time that remains, and we're right on track. So. Huh. Yeah. Well, anyway, I do have to post a YouTube lecture Wednesday because next Wednesday I've got jury duty. So that will happen. I guess you need to schedule some time at school to watch it, Malia.
That's okay. As long as you're not posting things that we can only watch over Thanksgiving break. I haven't done that here at Liberty, but it's not in Indiana.
Well, whatever I post, it should be posted before Thanksgiving break, I would hope, yeah. So,
As long as you post it semi.
what is Mission 8 on anyway?
All of chapter 7, some chapter 8, some chapter 9. Given that we're just starting chapter 7.
Oh, well, I can make Mission 8 due after Thanksgiving break. That's probably what you wanted, right?
Then there's also a quiz and a test after Thanksgiving break on the stuff that we're covering theoretically for 5.
This should be okay.
Do you want me to stop this?
Oh, yeah.